really interesting, but also abstract and kind of difficult concept in statistics called the sampling distribution of the proportion. So I want to start by talking about what proportions are and the difference between a sample proportion and a population proportion, and then we'll move on to the sampling distribution as well as the central limit theorem, and we'll do a couple of examples. So what's a proportion? Well, often we want to know what proportion, which just means percentage, what proportion of a population has a certain characteristic. For instance, what proportion of the U.S. population voted in the most recent presidential election? This population proportion is too big to count directly, right? Like we can't go and ask every single person in the entire country whether they voted last year or last election or not. So as usual, what we do is we take a sample. We take a sample and then we calculate the proportion of voters in the sample and hope that this sample proportion closely approximates the population proportion. So we want to know the proportion or percentage of people in the U.S. who voted in the last election. That's too big to count directly, so instead we take a sample, we figure out the sample proportion, that's the percentage of people in the sample who voted, and we use that to approximate the true population proportion. Now, in order to distinguish between these two proportions, that's the proportion in the sample and the true population proportion, the proportion in everybody, we have two different symbols. One of them is this thing, so here they are. This guy right here, that's pronounced p hat. It's like a p with a little hat on top of it. That is the sample proportion. Little p without a hat is the true population proportion. And so the goal is that we use p hat to estimate p. Okay. All right, well now let's talk about the sampling distribution of the sample proportion. So imagine the following scenario. It's a little bit weird. It's a little bit of a theoretical construction, but let's just see how it goes. Given a population, again, let's say of all U.S. persons, we can choose a random sample of size n. Maybe n is 100 or maybe it's 1,000, but let's say we choose a random sample of size n, and then we ask what proportion of our sample voted. Call that sample proportion p1 hat. Now, the reason I'm giving this a subscript here is that, as you're about to see, I'm going to generate more than one sample proportion in this like story. So in order to distinguish this sample proportion from the others, I'm calling it p1 hat. Okay. All right, so we take a random sample, compute the sample proportion, we call that p1 hat. Okay. Then we do it again. We choose another random sample, again of size n, and we ask what proportion of this sample voted. Okay, now that's probably going to be a different sample proportion, right? I mean, there's just some randomness involved. You're not going to get exactly the same proportion as the first time. So we call this new sample proportion p2 hat, okay, the second sample proportion. And over again, we choose random samples of size n, and we write down the sample proportions, okay? We do it, not just 3 times or 4 times, but we do it like 1,000 times. We do it 1,000,000 times. We do it 100 million times over and over again, really until the end of the universe. We're collecting samples and writing down the sample proportion. Okay? If you do that, then what you will wind up with is a list of numbers, right? A list of all the sample proportions that you obtained, right? P1 hat, P2 hat, P3 hat, and this list keeps going. It's a huge list of numbers. Now, this set, because it's a big, long list of numbers, it is itself a data set. Okay, it's a data set, and it has a name. It's called the sampling distribution of the proportion. So this object here, this object that you get by repeatedly taking samples and computing the sample proportion over and over again, that's called the sampling distribution of the proportion. Now, because this thing is a data set, there are some basic questions that we might be interested in, like, what does this data set look like? Is it normal, Like, is it symmetric? Is it skewed? Maybe it looks like this, right? That's not symmetric. That's kind of skewed in one direction. Or maybe there's like two peaks like that. Or like, what does this data set look like? What is the mean of the data set? If you take all these sample proportions and find their average, what do you get? What is the standard deviation of this data set? Remember, standard deviation is a measure of the spread in the data, right? So we could ask, like, how spread out is this data set? So lots of questions that we can ask about this data set, about the sampling distribution of the proportion. Most of those questions are answered by a really important theorem, maybe the most important theorem in statistics. It's called the central limit theorem. Okay, so what does the central limit theorem say? This is kind of a baby version of it, but it's good enough for our purposes here. What it says is for sufficiently large n, in other words, if the sample size is big enough, the sampling distribution of p hat, that's this weird data set right here that we've constructed, that data set approaches a normal distribution. Okay, so if n is big enough, then this data set looks more or less normal. Technically what's happening is as n gets bigger and bigger, if you take a larger and larger sample size, the larger sample size you use, the closer this data set actually looks to true normality. Okay, additionally, the mean of this data set. What is the mean of this data set? It happens to be the true population proportion, little p. Now, why does that make sense? Well, because look, there's some true population proportion out there, right? Like in our example, that's the true percentage of people in the last election who voted, okay? And you're taking samples, and you're writing down the sample proportion over and over again, okay? Now, when you take a sample and write down the sample proportion, P1 hat, it's probably not going to be equal to the true population proportion, right? Like if the true percentage of people who voted is 60%, then your sample proportion is probably not going to be exactly 60% because there's just randomness involved. Could be a bit above 60%, could be a bit below, right? But here's the thing. If you do that over and over again, if you repeatedly take samples and you keep computing a sample proportion over and over and over again, yes, sometimes it's going to be above the true value of p and sometimes it's going to be below. But if you take the average of all of these numbers, you're going to get p, right? You're going to get the true population proportion. So the fact that the mean of this data set is little p, the true population proportion, not surprising. That makes sense. And we can also ask, what is the standard deviation of this data set? The answer is not so obvious. The standard deviation, which is a measure of the spread in this data set, the standard deviation is represented by the symbol, this guy right here. This is a sigma. It's a lowercase Greek letter, right? Except it's got a subscript with p hat. It's sigma sub p hat, okay? That's the standard deviation of this crazy data set we've constructed. And what is it? Well, it's given by a formula. It's given by this formula right here. Square root of p times 1 minus p over n, where, remember, n is the sample size, p is the true population proportion. Where that comes from would take us a little bit too far afield. It's not too hard to explain where it comes from, but this lesson's already long enough. So we'll just take it on faith in this class that this is the correct formula and not really inquire too much about where it comes from. A quick note on this formula. One thing that you should notice about it is that it involves little p, right? That's the true population proportion. In realistic, like real-life cases, we will often want to compute this thing for various reasons, but in real-life scenarios, we typically do not know the value of little p. The true population proportion is usually what we're trying to estimate, right? I'll give you lots of sort of hypothetical problems where you know the value of little p, like I just tell you. But in real life, you often don't know what little p is. And so you need to compute this thing sometimes, even though you don't know what little p is. So what do you do? What you do is, instead of using little p, you use p hat, right? The sample proportion. So like in a real-life situation, you have one sample proportion. Don't get confused. Like this theoretical construction where we took samples over and over and over again, that is a way of explaining what this data set is. In real life, you don't take a million, billion, trillion samples and do this over and over again. You do it just once, and you just have one p hat, okay? So in real life, if you're trying to compute this thing and you don't know little p, and you have one sample only, then you use the sample proportion in the formula instead of little p, right? Because p hat hopefully approximates p. When you use that approximation, this thing has a different name. It's technically no longer called sigma sub p hat. It's called SE sub p hat, which is SE stands for standard error. So this is the standard error of p hat. So basically, this thing, the standard error, is used to approximate this thing when you don't know the true value of p. Okay, that's the idea. We won't do this too much on today's worksheet, but it will come back later. So, all right. So let's do an example. Okay. So I'm gonna go over this example here, and then I think I'm also going to do number 1 with you. Because if you're watching this video, you probably missed class, and this is something that you should have done in your group, and it's kind of something you really need to think carefully about. So let's have a look at the example. The example says about 58% of people voted in the 2012 presidential election. Let's just first think about this. 58%. What is that 58%? Is that p or p hat? Is that the true population proportion? Like, is that everybody, or is that just 58? So yeah, what I want to convince you of is the fact that if out of your 49 people, 23 of them or fewer voted, if exactly 23 out of the 49 voted, then your sample proportion would be 23 out of 49. Does that make sense? I mean, the sample proportion is a percentage. So if 23 out of the 49 people voted, then your sample proportion would be 23 out of 49, which as a decimal is like 0.46938, so like 46.9%. Okay, now let's think carefully about this. We're being asked, what's the probability that 23 people or fewer in the sample voted? Okay, that is like asking, what is the probability that the sample proportion, p hat, is less than or equal to this number right here, right? Because if you get exactly 23 out of 49, that means your sample proportion would be 0.46938. They're asking, what's the probability that you get 23 or fewer people in the sample having voted? That means that you'd be looking at what's the probability that p hat, your sample proportion, is less than or equal to this 0.46938 number, okay? Now, here's the thing that you have to understand to solve this problem. This is the most important thing, and it's maybe the hardest thing to grasp. Let's recall the sample proportion. Or, sorry, let's recall the sampling distribution of the proportion. P1 hat, P2 hat, P3 hat, forever and ever. What is that thing? Like, what is this data set? It is, yes, it's the list of what you would get if you took samples and computed the sample proportion over and over and over again. But one important way of thinking about it is the list of every possible sample proportion that you could obtain. Okay? It's the list of all possible sample proportions, okay, that you could theoretically obtain. Now, going out and actually collecting 49 people, okay, in your sample and looking at the sample proportion, that is the same thing as choosing a random element of this data set. That's the most important thing to understand. Okay, this is the list of every possible sample proportion that you could conceivably get. And by going out and actually grabbing 49 people and computing the sample proportion for that specific sample, what you are essentially doing is choosing one of the possible sample proportions. Okay, you're choosing one of these things at random. So by going out and choosing a sample and computing p hat, you are in fact choosing a random element of this data set. Okay, that's the thing to understand. So this question really amounts to the following. You go and you choose a random element of this data set. what is the probability that it is less than this number right here? That's what it's all about, okay? So really the question is, choose a random element of this data set. What's the probability that it's less than this number? Choose a random sample proportion. What's the probability that it winds up being less than 0.46938? Okay, that's the question. Now that is a relatively straightforward sort of normal distribution question, okay? Because we know a lot about this data set. We know that it's normally distributed according to the central limit theorem. We know what its mean is. We know what its standard deviation is. We're choosing a random element from it, so we know how to do this, right? So here's the idea. You've got this data set, this thing right here. It's normally distributed. It's centered around what is the mean of the distribution. The central limit theorem says the mean of this data set is the true population proportion P. Well, that's 0.58. So we have 0.58 right in the middle. And we're asking, you choose a random element. What's the probability that it's less than 0.46938? That number, 0.46938, is maybe like right here. 0.46938. And as you hopefully remember, the probability that your random element is less than this number will just be the area under the curve to the left. Okay, so whatever that area is, that's the answer to our question. Now, we know that to find this area, we have to convert to a standard normal distribution, right? This is not a standard normal distribution. The mean isn't 0, it's 0.58, right? So we have to convert using the z-score formula, right? Now, if you look at the z-score formula, that's z is equal to x minus the mean of your distribution over the standard deviation of your distribution. X is the number we're trying to convert. We know what that is. It's 0.46938. The mean of the distribution, we know what that is. That's 0.58. The standard deviation, though, we haven't computed yet. That's the sigma sub p hat. That's this thing right here. So we actually have to go and compute that. Okay, here's the formula. On the worksheet, I've just plugged in the numbers, like little p is 0.58, so you plug those in, n is 49, and that works out to be 0.0705, okay? So we replace x with the 0.46938, we replace the mean with the mean of the data set we're working with, that's little p, that's 0.58, and we replace the standard deviation with 0.0705, and we get this. And we find that z is equal to negative 1.569. Okay, and we can use our table to answer the question, under the standard normal curve, what's the area to the left of negative 1.569? So this area right here, that's going to be obtained just by looking at our table, which I'll skip the details. If you look at the table, if you look at the area value for z equals negative 1.569, that's like negative 1.57 approximately, right? You get 0.0582. So that's about 5.8%. So that's the answer to the question. Okay, so let's just run through number one together. Number one kind of holds your hand a lot and guides you through the thinking behind this, but let's just do it together, and then we'll be done. So it's a very similar problem to the one we just did, except it's kind of broken down into steps for you. So it says, suppose 30% of the population has a certain gene, a random sample of 50 people is chosen, the sample proportion p hat is computed, then another 50 people are chosen, and again p hat is computed over and over. You take samples of 50 people and compute p hat. You do this thousands, millions of times. Then you have a list of all possible sample proportions, p1 hat, p2 hat, p3 hat, and so on. Part A, this data set that we've just constructed, it has a name. What is it? It's the sampling distribution of the proportion, right? That's just the name of it. Sampling distribution of the proportion. Now, what is the mean of this data set? Like, what is the average of all these numbers? The central limit theorem says that the mean of this data set is, in fact, the true population proportion little p, which in this case is 30% or 0.3. Okay? What is the standard deviation of this data set? Again, the central limit theorem says the standard deviation of this data set is what we call sigma sub p hat. It's given by the formula root p times 1 minus p over n. Little p is 0.3, n, the sample size is 50. Okay, if you plug all of that in, you get, I'm just going to look at the answer really quickly because, I mean, it's not hard to do on your own. It's 0.0648. Okay, if you plug everything in. 0.0, what was it? Why can't I keep a number straight in my head for more than 2 seconds? 0.0648. Okay, so that's the standard deviation. D. Suppose a random element of this data set is chosen. What's the probability that it's less than 0.25? Okay, this is just a very straightforward normal distribution problem. The central limit theorem says this thing is normally distributed, right? So it looks like this. The mean is, 0.3. Okay, we know the standard deviation of the data set. It's this number here. And we're being asked, what's the probability that a random element is less than 0.25? So 0.25 is maybe here. And the answer to that question will be simply the area underneath the curve to the left of 0.25, okay? So you have to convert to z-scores, right? You do z is equal to the number we're trying to convert, that's 0.25, minus the mean, which is 0.3, or the standard deviation is 0.0648, which I think I have in the solutions, comes out to be like negative 0.77. And if you consult the z-table and look at the area under the standard normal curve to the left of that number, you get like 0.2206. So 0.2206. Okay, so 22.06%. Okay, is the answer to that question there. Part E. Suppose you choose a sample of 50 people and compute the sample proportion. This is the same thing as choosing a random element of this data set. Convince yourself of this. This is what we were talking about before. This data set is nothing but the list of all possible sample proportions. So by going out and taking a sample, a specific sample, and computing a specific sample proportion, you are essentially choosing a random possible sample proportion. In other words, you're choosing a random element of that data set. Okay? F. Suppose you choose a sample of 50 people. What's the probability that the sample proportion is less than 0.25? This is the same question in part as we did in part D. Okay, this is really what I need you to see. That by going out and taking a specific sample of 50 people and computing the sample proportion for that specific sample, you are essentially choosing a random element of this data set. Okay? So me asking you what's the probability that your sample proportion is less than 0.25 is the same thing as me saying go choose a random element of this data set. What's the probability that's less than 0.25? That's exactly the question that we answered in D. It's exactly the same question we answered in D. So you don't have to redo all this. It's just 22.06%. Oops, too many zeros. 22.06%. Yeah, so you really got to convince yourself of the logic here. Okay, if you can do that, then what you're supposed to do and why you're doing it will totally make sense, and you won't forget what you're supposed to do. If you just try to like follow the steps and like use the formulas and memorize it, like, oh, first I do this, if you don't really understand it, then you'll be making lots of mistakes and you'll forget it really quickly. So really understand this. Okay. Okay, that is all.